But is that reality then? If we can't even study it, understand it, live in it, comprehend it, observe it, is that reality? Then you get into definitions. You always do. In philosophy, you certainly do. Hey folks, welcome to Trickle Down Philosophy. I'm Don. I was a philosophy major at Rutgers back in the day, and I kept my curiosity for learning, and that's what this channel is about. And I'll look at virtually any topic, ranging from theology to science to, atheistic perspectives and so on. And in this one, and I love looking at the sciences and just continuing my learning in all these. And so you're going to learn with me. Andrea Schulman is explaining what is quantum physics, and as opposed to classical physics. So that's how she breaks it down. Maybe that's how it's commonly broken down. But quantum physics is about the small, the incredibly tiny. Here we go.
Hi, this is Andrea Schulman again, and yes, you are smart enough to understand quantum mechanics, even if you don't identify as someone who is traditionally book smart. Today's video is entitled Quantum Physics for Dummies, and I really hope that you enjoy it. But first, if you are excited to watch today's video, please give it a thumbs up, and also please remember to subscribe and comment. Your engagement promotes my work and keeps me in business, and I truly do appreciate it. All right, let's go ahead and break down quantum mechanics in a very simple way. Now, the first thing to understand about quantum physics is that it's different than classical physics.
Right.
Now, classical physics is really about how physical objects move. All right, so physical objects like this tennis ball, how do they move? Quantum physics, however, focuses on quantum particles. Now, what's a quantum particle? It's a very fancy name for something you probably learned of in school, which are the building blocks of matter. See, if you've heard of something called a proton, a neutron, an electron, a photon, those are examples of quantum particles, although there's many other kinds of fancy quantum particles as well. But for the sake of this video, all you really need to know is that a quantum particle is the building block of matter. Okay, so if you take physical matter and zoom in with a really high-powered microscope, if you get inside deep enough, what you'll find is that physical matter is made up of atoms, which are in turn made up from quantum particles.
The crazy thing, not crazy, but the fascinating thing about this, and it is a thinking person's game, is if matter is all comprised of basically non-physical objects, how do we get physical objects out of it? And basically when you get into it, the reason neutrinos pass virtually straight through the earth and everything is because virtually everything is comprised of empty space. And certain objects are harder than others. Physical, right? That's what we describe as physical. If I stub my toe on a wall, it's hard. Or if I drop a tennis ball on me like she's got, it has one effect. If I drop a lead marble on my toe, it's another effect because it's heavier, it's denser. But the way the quantum particles are bound together inside it determines whether something has greater density, greater weight than others, like on the periodic chart of the elements and so forth. But it is sort of a conundrum that everything that we see here, the building blocks of what we call matter, basically don't have much mass at all.
And so while classical physics focuses on how matter moves, physical matter moves, quantum physics really focuses on these building blocks of matter, the inside of the atoms. How are those particles moving? Now, physical matter behaves in a relatively predictable way when we look at it through classical physics. If I let go of a ball, it'll drop to the floor. And so if you think of, in school, maybe you learned of Isaac Newton and that story of the apple falling on his head. That's really classical physics. And again, it's very predictable. So if I understand the size and the weight of this object, and I know that I'm throwing it at 10 miles an hour, and I know the approximate wind velocity, I can reasonably predict how long it's going to take this ball to travel a given distance. And because we can see physical matter, we're very familiar with it behaving in a very predictable way. But while physical matter in classical physics behaves in a very predictable way, when we zoom on in and start looking at quantum particles do not behave in a very predictable way. And understanding.
And that's because we don't understand it yet, but the goal obviously is to understand it more. And that's just the nature of scientific inquiry. Like, how do we figure this out? We love to figure things out. Anytime there's something we don't understand, we got to put our brains to it to figure it out. We're just a very curious species.
The basics of quantum physics and how quantum particles move will give you a very strong appreciation for how your reality is constructed, how physical matter is constructed, and what you can do to change physical matter, change reality in your life if you want to see things behave differently. So, how do quantum particles move? In a word, infinitely. See, in other words, if you drop a quantum particle, it doesn't just drop to the floor. It goes everywhere. See, it has been strongly suggested that quantum particles don't just exist in a particular location, but rather they also exist in something called superposition. Superposition basically means existing in many places at once. Superposition can also be described as being kind of like a wave or ripples. And so in essence, something like a photon could be seen or exist in a particular location, but it also simultaneously exists as a wave or as ripples throughout the universe. Now, if this sounds far-fetched, there is scientific justification to this claim. And if you'd like to learn about the scientific justification for the claim, I'd highly recommend looking into an experiment called the double slit experiment. The double slit experiment builds on an experiment created by Thomas Young in 1801, but since then it has evolved into a much more technical experiment. The long story short about the double slit experiment is that if you take a photon or an individual particle of light, a quantum particle of light, and shoot it off into space, if you don't directly look at it, if you don't directly observe it, it travels as a wave. You can pick up feedback of an individual photon across space. However, if you take a really fancy high-powered microscope and zoom in on the photon and watch it as it travels out into space, it will travel and appear to be one particular particle.
Well, that's because you've set it up that way too in this description, where you get a high-powered microscope and you focus on just the one. Of course, it's going to look like just the one. A different experiment that I'd like to sort of understand more about is that light travels 186,000 miles per second, right? If you were to set up a light switch in New York, the switch is here, and have a 3,000-mile copper line, conductive line, say going to LA, and there's a lamp there, and you're going to turn the switch on here in New York, how quickly would that light come on? And it's roughly, I think, 96% the speed of light. It would still be almost instantaneous. These electrons get excited so quickly that it's almost instantaneous, even going through copper. And that's the world of the small. Why is that so conductive, so excitable within that medium that it travels at almost the speed of light?
But this is only the case if you are directly observing the photon, which fortunately today science allows us to do. But the trick is you have to be looking at the particle. If you look at a photon particle, it exists in one place. But if you collect data on that particle without observing it, it appears to exist in many places in a wave pattern all at one time. In other words, an individual photon only becomes an individual if an observer like you or me is looking at it. If there is no observer of the photon becomes infinite.
Kind of gives us a special place in the universe, doesn't it? There's something off about this. There always has been, because I've known about this, and there's something very much off about the impact that our observation on things has. At some point, I'm going to look more into this and be able to articulate why that is problematic. I know it has been described in such a way as problematic, that why is it that just us merely looking at something seems to impact its behavior? Some things aren't even observable when we look at them.
And so you and I as observers, what do? We collapse the infinite into the physical. So what does quantum physics tell us about our physical reality? Well, matter, physical matter, is made up entirely of quantum particles. And if quantum particles exist in superposition, meaning the quantum particles exist everywhere at once, guess what that means about the tennis ball? It too exists everywhere at once. And this is why many scientists today believe that there isn't just one reality, but rather there are many realities. And some scientists go as far to say there are infinite realities, the ones that we experience.
But is that reality then? If we can't even study it, understand it, live in it, comprehend it, observe it, is that reality? Then you get into definitions. You always do. In philosophy, you certainly do. You've got to, in any field, what's your definition? Like somebody recently asked me on the channel if I believe in God. And because I say that I'm agnostic. The person, I don't know if they're a subscriber, but the viewer said, do you believe in God? You say you're agnostic, but do you believe in God? And I gave my answer. I said, I leave the possibility that there is one, but I cannot prove or disprove one. And the response came back that, well, I didn't ask you if you're open-minded. Do you believe in God or not? And I said, well, then, one, I've already given you my answer. I suppose you need to get down to the nitty-gritty about what do you mean by the word believe? Do you mean I have absolute certainty about something? And my response was, no, I don't have absolute certainty, because I think certainty is an absurd notion. I don't think there is such a thing as certainty, because we have things that we believe, not just in the theological realm, but in the scientific realm and the observational realm. And this, what Andrea here is saying as well, sort of has similar undertones, if you will, where what is the reality? If there is an infinite number of realities, does reality exist? How do we define reality? And these get into other questions, and that's why philosophy is a lot of fun, because it keeps a curious mind going.
Are the ones that we have collapsed into place. So how can understanding quantum physics change your reality? Well, you are the observer. You are what collapses the infinite into the specific. How you choose to observe the world, what you focus on, what you look for, directly impacts the reality that you're living in. Your focus is what's collapsing the infinite into the specific. And therefore, learning how to change how you observe can completely change the world that you live in. And if this excites or intrigues you, I would recommend that you check out another video that I have created entitled 2 Ways to Quantum Leap Your Reality. And I will try to remember to put a link to that video in the description of this one so you can check it out next. Thanks so much for watching today's video on quantum physics for dummies. Again, if you enjoyed this video, please give it a thumbs up.
All right, I'll put the link to her channel in the description box below too, because I like the effort that she put in. I don't know what her background is. Maybe I'll look in her channel and see, what her background is and all that. But I like the explanation. I like learning these things. And some of you people already know some of this stuff. Others are learning along with me. And some of the stuff I already know because I've studied it. But some people put things in certain perspectives, and that perspective helps coalesce another perspective and sort of give you more of a cogent idea of what we're talking about here. But quantum physics is just about the world of the small. And we would hope that the world of the small mimics the world of the larger, which would mimic or be the same in physical attributes and properties and laws, if you will, as the largest, and galaxies and so on. But there's just a lot we don't know. There's a lot that we cannot observe, and it's fascinating that we cause things to disappear sometimes by focusing on them. But I do like, it was almost like Cartesian, like Descartes, where I think, therefore I am. But when you talked about that, we are things coalesce into us, into our being individually, and that enables us to observe things. And there's a circular or tautological, everything basically can be reduced to a tautology, but and maybe that is the way we think, and that it's not necessarily a negative. For a formal logician, a tautology is not a good thing, because you're assuming the premise and the conclusion, and then the conclusion circulates back into the premise, and it just sort of goes round and round and round. You need a third term in there to sort of make it a legitimate argument or valid argument. But still, it's kind of almost inescapable, like survival of the fittest. Well, who are the fit? The ones that survive. Why did they survive? Because they're fit. And there's a tautological aspect of it. So you need a third term in there to actually give you more information to escape the circularity. But in this case, nonetheless, I mean, it's hard to gainsay what Andrea just said, that sort of like, we're the observer. I observe, therefore I am. Maybe that's how we should run with this. All right, folks. Like she said for her channel, please subscribe to mine and help move this thing along. Keep the learning going. Have a great day. See you on another video. Keep thinking philosophy.